Hello, my name is Zhuoling. I'm a PhD student at King's College London doing computer science. I'm going to introduce a piece of work about planning the harvesting sequence in complex environment for strawberry picking robot. Strawberries are planted widely around the world and are an important cash crop, but strawberry farming has quite a high labor cost. These costs motivate a strong need for a strawberry harvesting robot. Comparing with hardware design, my research interests are more about the controlling system, especially about improving the efficiency of the robot. The basic process of fruit harvesting could include tasks such as identifying mature strawberries ready to pick, controlling the robot arm to approach the target, and removing the fruit from the plant. So far, the major bottlenecks in current strawberry harvesting robots are single image detection rates and harvesting cycle times, especially in complex cases. Below here shows some examples about strawberry targets. From left to right, the complexity is increasing. You can see in the simple cases, the strawberry is not covered by anything and its neighborhood is very clear. It is easy to detect and also easy to reach with a gripper. However, in the complex cases, the strawberry might be covered by other strawberries and is very hard to be detected, also very hard for a gripper to reach to a picking point and detach it from the stem. In reality, when harvesting with a robot in real farm, the complex cases are challenging, but it's unavoidable. Many researches have been done to improve the image detection rate. Different methods are introduced to detect the target object, and the mainstream research on fruit detection can be roughly divided into two phases. First, detecting with traditional computer vision methods based on shape, color, or hybrid method, and the second, detecting with machine learning methods. To reduce the cycle time, a possible way is to improve the harvesting sequence. So far, there are sorting using traveling salesman paradigm or using heuristic methods like sorting from low position to high to suit gripper working mode and some other methods. All of them has their advantages and disadvantages, of course. For example, traveling salesman paradigm usually reduces more time than heuristic methods, but the computation could be slow, especially when there are lots of strawberries as targets. In our work, we hope to develop a method by learning from human decisions and calculate faster than applying traveling salesman paradigm to a bigger number of targets. A video game was made to collect data. It is a convenient way to collect data from human user when people are socially distancing. The arrangement of fruit in three-dimensional is simulated from the distribution of strawberries in elevation and plan views respectively. Here's an example on the left, like two images from the data set. So the model is derived from a dataset that includes 1,143 images of Dorisco's Amnesty strawberry. The images are taken by a robot in 2019 in some polytunnels at Rice Home, Lincoln. The images, including 186 taken from bottom of the plant, and all the rest of them are taken from in front. They altogether contains labels for 2,997 ripe strawberries, as well as 34,101 unripe strawberries in total. The number of ripe and unripe strawberries follows the pattern in which they appear in each image. The strawberry plant model used in the video game ignores leaves and only presents the distribution of the strawberry. Because of the technical issue, it is very hard for us to present a whole strawberry plant with all its fruit randomly generated, and also because the task we are interested in is only really concerned with the strawberry themselves rather than the leaves or roots of the plant. The strawberry model were created using a software called Blender and can be easily distinguished from each other by their colors. So you can see the strawberry models here. The obstacles in the game include green strawberries as well as rotten strawberries. Overall, the model is designed to represent scenes that a robot could view when working during the harvesting period of Amnesty strawberries. The video game is a WebGL project created with Unity. The game, we call it Strawberry Hunter, is uploaded to a web page so the users can play the game easily with their own devices, even during social restrictions. Here is a screenshot of the game menu. When start the game, it provides 3 different modes: training mode, easy mode, and hard mode. Training mode introduces the game to the user and help them become familiar with the way of operations. We suggest users to start with the training mode first to make sure they are providing good demonstrations in easy mode and hard mode later. In all modes, the user can shift their viewpoint in the game. This viewpoint is that of a robot. It will be referred to as moving the camera in this video later. Easy mode simulates human strawberry picking by requiring user to click on the ripe strawberry to harvest it. When the mouse is on a strawberry, it will glow to help avoiding clicking on a strawberry unwanted by mistake. When click on too much wrong strawberries, user will lose the game, unfortunately. Here is an example of an easy mode game. The user needs to collect all the ripe strawberries to win the game. To help select good demonstrations for further research, if a user collects unripe strawberries or rotten strawberries by mistake, they will lose points. Hard mode simulates harvesting by a robot gripper. Thus, the user needs to move the gripper with keyboard to a suitable area above the target strawberry and then press a key to harvest it. Here is an example of a hard mode game. There are 4 parts of data collected anonymously. First, the score. It presents how well the user is collecting strawberries. Collecting unripe or rotten strawberries will lead to losing points. The score is checked for each game later, as game records with mistakes are not considered to be good demonstrations. Only game records with a full score are used in our analysis later. And the strawberry map. It is all the strawberry fruits' location and their type. So red ones as target, not red ones as obstacles. Also, strawberry collected order. That is, when is each strawberry being collected since the game started. The last one, movement record. So when and how a gripper is moving in the hard mode and when and how a camera is moving in the easy mode. The operation data for each player who played the game, including score, strawberry map, player movement, and order of strawberries chosen, is collected anonymously and sent to a cloud database after each round of the game. And it is cleared from the cloud storage and moved to local storage at intervals for safety reasons. To analyze the user's preference when collecting strawberries, anyone above 18 is welcome to take part in the experiment. The ethical approval is granted to this research already. In each game, ripe strawberries are collected in sequence. When a ripe strawberry is selected, it is considered to be better than all the others in that situation. We call each situation in which such a choice is made a scene. As an example, in this scene, strawberry 1 in the blue circle is selected. There are 3 target red strawberries in this scene and 3 obstacles around them. To simplify the description of each scene, the selected strawberry in a certain scene is then paired with all the other ripe strawberries in the same scene. The choice made by the user means there is always a preference between each pair of strawberries. For example, here the selected strawberry 1 in the blue circle is paired with strawberry 2 and strawberry 3 respectively. Strawberry 2 and strawberry 3 are less preferred than strawberry 1 in this scene according to the behavior of the user for picking the strawberry 1 first. The order of strawberries in a pair is randomized. Using this preference, we can then construct a whole harvesting sequence in a way similar to the bubble sorting algorithm when applying our method to multiple targets. We will show that later in this video. To describe the strawberry and the environment more precisely, some parameters are considered. First, distance parameters are calculated. The distance from previous collected strawberry to target in three-dimensional and the distance from the player to the target in three-dimensional. Left here, the strawberry in yellow circle is the target strawberry, and this grayish shadow strawberry is the previously collected strawberry. It's an example to show how to calculate the distance from previous collected strawberry to the target. Also, the location of the player for the purpose of this distance calculation is the position of the camera in easy mode and the position of the gripper in hard mode. Here is an example on the right-hand side. Second part is the visibility parameters, which include if the target is in the field of view of the camera, the number of obstacles between player and the target, and the percentage of the target as that is visible. In this example, target strawberry is the red strawberry in the yellow circle in the middle. Upper left image shows it is visible from the viewpoint of the camera. Upper right image presents there is one obstacle between the camera and the target, which is that green strawberry in the red circle, and the percentage of the target that is visible is calculated shown as image below here. Of course, the visible area is just an approximate value. The third part of parameters are about the space around target. As shown in this example, the space around the target is divided into 27 cuboids, which is 3 by 3 by 3. So the central cuboid contains the target, and the type of the obstacles in each cuboid is recorded and flattened into a list as shown in this slide. So here in this example, if a cuboid contains red strawberry in it, it's recorded as 1. If there is a green or rotten strawberry containing by the cuboid, it will be recorded as 2. You can see the numbers here. So the parameters for the two strawberry in a pair are placed together to become a vector, and the vector is labeled depending on the order of the two strawberries. So if the first strawberry is collected earlier by user, the vector will be labeled 1. Otherwise, if the second strawberry is the one that be collected first, the vector will be labeled 0. As shown in this example, strawberry 1 is a preferred strawberry before strawberry 2 and strawberry 3. So in the left example, the vector is labeled 1, and in the right example, the vector is then labeled 2. A neural network with two fully connected hidden layers are chained on the data with such format. When using this neural network for classification, feed a parameter vector generated by two strawberries parameters into it. If the output is 0, then the second strawberry should be collected before the first strawberry. And applying this to all the red strawberries in a map, there will be a possible sequence for harvesting all of them. This is the information on the dataset collected from the game until April this year, and it's shown in this table. So we consider data from easy mode games that had just 2 and 3 ripe strawberries as separate from data gathered from other easy mode games. So here we have 4 data sets: 2 strawberry in easy mode, 3 strawberry in easy mode, and other easy mode games, and the hard mode. The accuracy of the neural network chain on each dataset is shown in this table. The highest accuracy is 98.80%, both chained and tested on 2 strawberry easy mode game results. Comparing different rows, it is noticeable that the 2 strawberry dataset is the best choice to train a robust classifier. There is also a clear difference between easy mode results and hard mode results, as classifiers trained on 2 strawberry mode work very differently on the hard mode dataset comparing with other easy mode datasets. We also tested the sorting method on a small number of examples. Here we used A* for path planning, a heuristic method like sorting from near to far, and our neural network sequence sorting method are both applied to target sorting and then compared. They are tested on 137 groups of data following the distribution of our strawberry fruit model. As a result, our neural network sequence sorting method works better on 63 examples, which is 46%, and in 37 examples, both methods perform the same. Only in 27% of the cases, our neural network sequence sorting method is worse than the heuristic method. Here are 2 examples that our heuristic method works better. So in these 2 images, the green circles are the obstacles, could be green or rotten strawberries. The red circles are the red strawberries. Blue line here shows the path following the harvesting sequence sorted by our neural network sequence sorting method, and the teal line here shows the path by the heuristic method. As a summary, we describe a video game simulating strawberry harvesting to collect human demonstrations. The experiment suggests that human harvesting following a pattern, and that can be retrieved from the data collected so far, and we plan to use this in future research on task allocation in harvesting. And the low accuracy of a classifier trained on the hard mode dataset may be due to the small dataset, so we first plan to collect more data to provide clear conclusions about human working patterns. When tested on some examples as a pilot study, our sequence sorting method works well, but still have some space for improvements. More experiments will be carried out in future research. So, okay, hope you find this piece of work interesting. If you are interested in trying the video game, you can find it following this link. Thank you for watching.